Hey class, and welcome back to Prelab number 5. Can't believe we're this far in the semester already. So let's go ahead and talk about conservation of energy and these few example problems that we have. And I want to start by jumping into question number 1. So here we're shown a graph of force versus displacement for a spring. And as we've talked about in class, as you pull on a spring, it gets harder and harder to pull it each little inch or centimeter or millimeter even that it's pulled back. And so we know that there's an equation that governs the amount of force needed to stretch a spring, and that's just equal to K times X, because the force the spring exerts is negative K times X, since it's just in the opposite direction. So the first question asks us actually to figure out the work being done as somebody stretches the spring over some distance. Now, there's a trick here because normally we've been learning and we think that work is just equal to force multiplied by distance. However, that equation assumes a constant force or average force being exerted over some distance. So that's not actually going to work here unless we use the average force, which is not the maximum kx. That's only the force at the very maximum displacement. When it starts, the force is 0. So the average is going to be halfway. So there's actually two ways to think about solving this. The first is to think about average force times displacement. And the average force is going to be 1/2 kx, because again, the average force is the force right here at the halfway point, which is when x is, or the displacement is half of this maximum x value, and then it's multiplied by the total distance, which is x, and so the work would actually come out to be equal to 1/2 kx squared, which is the equation I gave you for the elastic potential energy stored within a spring. Now, the second way to do it is to think about work as just being actually equal to the area under the force displacement curve. So it would be the area of this triangle. And we know for a triangle, the area is 1/2 base times height. And so in this case, that would be 1/2 the base is just x, and the height is kx, the maximum force. And so once again, we get the work as 1/2 kx squared. So either way you do it, you get work equals 1/2 kx squared, and that's your answer for pre-lab question number 1. So now let's move into pre-lab question number 2. So in pre-lab question number 2, we're told that we have this ball that's being dropped, released from some initial height. It's going to fall down, hit the ground, and then it's going to bounce back up and return to a lesser height. And so we're told H initial is 3 meters and H final is 2 meters. And the ball has a mass of 1/2 kilogram. And then we're asked to calculate a series of different things. The first thing we're asked to calculate in part A is what is the speed of the ball just before the bounce. So if I think of this as kind of point 1, I'm going to consider right here just before it hits the ground as point 2, and then as it comes off the ground, we might call that point 3, and then up at the max height, point 4. So the cool thing is we can analyze energy transitions from 1 to 2, 2 to 3, 3 to 4, and so on. From 1 to 2, since it's just in free fall and we ignore air resistance, we can assume energy is conserved. So the total energy at point 1 should be equal to the total energy of point 2, since there's no outside forces taking away energy. So that means that the energy at point 1 is just going to be mgh initial, initial, and that should be equal to 1/2 mv2 squared, the velocity at point 2. So we can actually solve for v2, and it will just come out to be equal to the square root of 2gh initial, or v2 equals, I think it comes out to 7.67 meters per second, plugging in the values that were given. Box worthy for sure. Question B then asks us to figure out this amount of thermal energy, the energy that is converted into heat as a result of the collision. So again, from 1 to 2, energy is conserved, and then 3 to 4, energy is conserved, but between 2 and 3, energy is lost due to it hitting the ground. So if we look and we say, okay, well, the energy at point 1 plus any work non-conservative, outside forces that take away energy, will be equal to our total energy at the very end at point 4. And this work non-conservative right here, that is going to be the work thermal, or the energy that's turned into thermal energy. So that's the TH value that the problem's talking about. So what we can say then is that the thermal energy, the work non-conservative, let's just define it over here. Work non-conservative is just going to be our thermal energy we're trying to find. And so our thermal energy is just going to be equal to whatever energy you have at 0.4 minus your energy at 0.1. And so the thermal energy should just be equal to mgh final minus mgh initial. And so if you plug in your values, I trust that you all can do that. What you should have found is that this comes out to be negative 4.9 joules of energy, and it's negative because it's taking the energy away, right? And so really, if you wanted to answer the question when it says how much energy is converted into heat, that would just be the magnitude of your thermal energy. So it might just be asking for the positive 4.9 joules. I'll accept either positive or negative value there because the wording of the question might not be as crystal clear as it could be. All right, so now the last thing that we're asked to determine in part C is what is the speed of the ball at 0.3 right here. And so once again, since we know energy is conserved from 3 to 4, we can do E3 equals E4 and just have 1/2 mv3 squared equals mgh final. So you notice this should look very similar to what we did up here in question 1. And we get a very similar solution as we get here. V3 is just going to be the square root of 2gh final. And so it's the same as question 1, only now we have the 2 meters instead of the 3 meters. And so we get a slightly smaller final velocity of 6.26 meters per second for that one there. So that's questions 1 and 2. And so now for question 3, I'm going to flip back to the actual lab. So here's Prelab question 3. I'm not going to write or type anything. I'm just going to kind of talk through it so you can check your answers on this. So here we see this roller coaster situation, and we're given or told to discuss kind of these 5 points, A, B, C, D, and E, where the roller coaster is. So the first question asks us to sort of describe or talk about the kinetic and potential energy at each point. Clearly, the kinetic energy is going to be the largest when you're moving fastest. So that's actually going to be at the very bottom at point B, and also it'll be either equally high if we ignore friction and air resistance at D, or it'll be a little bit less due to some losses from B to D. But those are the places where your kinetic energy is going to be the highest. The next highest would be E, and then C and A would be the very lowest in terms of the kinetic energy. Potential energy, though, would be highest at point A, second highest at point C, third highest at E, and you'd have zero potential energy at B and D. And then B asks us, okay, what happens to the roller coaster's kinetic energy as it goes from B to C? Well, from B to C, the kinetic energy will decrease because it's going to be turning into gravitational potential energy. So again, if you're gaining one form of energy, it has to come from somewhere, either from another form of energy or from work being done outside. And so in this case, since we're treating this just as a free moving roller coaster with no external like motor or rocket boosters or engine or anything, then all of that gravitational potential energy it gains from B to C has to come from its kinetic energy. So the kinetic energy will drop, gravitational potential energy will increase as a result. Then question C asks us, why is it important that A is higher than point C? Well, the reason for that is if you analyze point C, at that point you will have gravitational potential energy, but you also must have kinetic energy because you have to be able to stay in your seat. You don't want to be falling out. So you need to have at least enough kinetic energy so that you have a centripetal acceleration large enough to be supplied by gravity and you won't fall out of your seat. So you basically need a v squared over r centripetal acceleration that's equal to or larger than 9.8 meters per second squared. And so you could actually calculate like the very minimum speed that would prevent you from falling out of your seat. You probably, if you're an engineer designing this, you'd want it to be a little bit faster than that. But that's why you need A to be higher so that you would still have gravitational potential energy, but some kinetic energy left. If all of your gravitational potential energy took 100% of the energy and there's no kinetic left, then people would start falling out of their seats. And then the last question is, why is it that the roller coaster would actually be losing energy over time and you wouldn't have, the exact same total energy at E? That's what I've been kind of talking about or alluding to throughout. Air resistance, friction, and those types of outside forces would take away much of the energy actually. So you need to have much, much more initial energy at point A to make it all the way through safely. So that's really it for this pre-lab. I hope that helps you out and gets you ready to rock and roll. As always, let me know if you have any questions and hope you have a great day.